Uh, okay, first introduction. For scope, we use 10, 20, 30, and 40 Newton masses. And for steel rod, we use steel, aluminum, and nylon. The length of use for the experiment is 200 millimeter and 400 millimeter. And the objective of this experiment is to investigate the relationship between torque and the angle of twist of a circular or rectangular cross-section bar, and to determine the modulus of rigidity of the material.
Okay, so for this experiment, its theory is related to the torque, the angle of twist, and our goal to find the modulus of rigidity, which the torque is the rotational analog of linear force, which causes a body to twist. The angle of twist is the amount of angular deformation due to an applied torque, and the the modulus of rigidity just summarizes how rigid or not rigid some material is. And for this experiment, we shall find the value of Ga by using theta equals to Tl over Jg, with T being the torque, L being the length of the material, J is the second moment of area, and G shall be the moment of the modulus of rigidity. Thank you.
So for the experimental setup for experiment 6, actually in lab, there will be two places to set up this experiment, but our group choose the place that only set up on the table. So as you can see in the slide, that at the left side it show the first place, and the second one is place that we choose, which is only on the table. So basically the apparatus that we use for this experiment is aluminium alloy rod, steel rod, nylon rod, and then spanner, digital caliper, ruler, load, and torsion bars testing machine.
Uh, Next methodology, which is procedure. For first step, the diameter of steel bar will be measured and recorded using a digital caliper. And next, the steel rod will be clamped onto the device, and load hanger will be placed on the cord. The rotational scale and pointer will be set 200 millimeter from the fixed clamp, and the pointer will be set to 0. And next, 10 Newton weight will be attached to the load hanger, and the amount of twist that occur to the bar will be recorded at table 1. And next, step 3 and 4 will be repeated by adding weight by 10 Newton increments. And next, step 3 to 5 will be repeated by setting the scale at the 400 millimeter mark from the fixed clamp. And lastly, step 1 to 6 will be repeated by replacing the steel rod with an aluminum bar and nylon rod. Next, result for steel. For steel, we use load 10, 20, and 30 and 40 Newton, and the angle of twist at 200 is 1, 2, 3, and 9 rad increase with respectively to the load, and the top is 2000, 4000, 6000, and 8000. And at 400 millimeter, the angle of twist is also gradually increased, which is 2, 8, 10, and 16 rad. And for the torque, the torque is 40,000, 80,000, and 12,000, and 16,000 Newton meter torque. And next, for aluminium, we use load 10, 20, 30, and 40 Newton, and at 200 millimeter, the angle of twist is 2, 3, 4, and 6, 5 rad. It increase with respectively to the load, and the torque is 2000, 4000, 6000, and 8000. And at 400 millimeter, the angle of twist is 2, 5, 7, and 9 rad. It also increases with respectively to the load, and the torque for for 400 millimeter is 4,000, 8,000, 12,000, and 16,000. And next and lastly for nylon, we use slot 2 Newton, 3 Newton, and 4 Newton, and lastly 5 Newton. This is because nylon it's too fragile, so use a lower load. And at 200 millimeter, the angle of twist is 6 rad, 10 rad, and 13, and lastly 15 rad. And the top is 400, 600, 800, and 1000 Newton millimeter. And at 400 millimeter, the angle of twist is 10, 15, 24, and 28, right? And for the top, 800, 1200, 1600, and 2000.
Okay, for the first discussion, from the fluff concept which we have seen earlier just now, we can say that the relation between the torque and twist of the rod is a linear relationship which follows the torque and twist formula. That theta equals to TL over JG, which in itself has a linear relation. And we can see that most of the data closely relate to approaches a straight line, which supports our argument as well. Thank you. We shall continue with the observation or analysis of the equation, which shows that the relationship between theta and t is linear. So we can plot the graph and see the trend line of our data in uniform, as we can see earlier, which the mathematical approach is y equals to mx plus c, where y represents theta and x represents t. And the slope is denoted as m, which was derived from the graph. So from the R-square statistical model, it explains how the dependent measure changes over time, with the zero meaning the model doesn't fit the data at all, and when it does have a correlation with the data. And from our data, we achieve a trendline value that is always above 0.96, which is close to 1. This means our trendline shows a linearity relationship between these two variables, which are t and theta, which absolutely prove our experimental data produce a linear relationship, which are high R-square value when plotting theta against t, and the experiment confirms the validity of our formula.
For the discussion part 2, which is the comparison between three different types of bars with different lengths of rotation scale and pointer from the fixed clamp. As the distance between the pointer and the fixed clamp increases, the angle of twist also increases. Each of the bar experiences increasing angle of twist as the weight of load increases. The increment of steel bar is the least, followed by aluminium at moderate, and finally nylon bar, where the increments are obvious. They can be arranged as follows, which is steel as the least, aluminium in the center, and lastly nylon.
So for the last question for our discussion, which is based on your finding, explain the relationship between the modulus of rigidity of material with the parameters such as type of material of the bar, for the bar, length of the bar, the shape of the bar, and the polar moment of inertia. So for the first one, we will talk about the material of the bar. So the explanation is modulus of rigidity varies with material type, which is the different material got the different modulus of rigidity. And then higher G indicate more resistant to shear deformation. So for this experiment, the material that got the higher G is steel, and then lower G indicate the softness of flexibility. So for our experiment, that have a lower G, which is nylon. The material that have the lower G is which is nylon. And then so for the comparison of material, so steel, and then we compare steel and aluminium. Steel has a higher G due to the higher carbon content, make it more resistant to deformation compared to aluminium. And then nylon as a polymer, nylon is less rigid than both steel and aluminium, resulting in the lowest G. So after we talk about material, we will talk about the shape of bar. So bar with a circular cross section, hollow or solid, have higher resistance to shear deformation. And then therefore circular cross section bar have a higher G compared to rectangular or triangular bar. So after that, length of bar. So length of bar also can what we call memberi kesan kepada value of G. So if we increase the length, it can cause a higher value of G. And then lastly is polar moment of inertia. Increase polar moment of inertia result in a lower value of G. That's all for question 3. So for the safety procedure that we follow in this experiment, so first, make sure the eye level are perpendicular to the scale of ruler when taking a reading. Second, wear a closed shoes to prevent any injury that caused by falling heavy object. And then make sure the floor is dry along the experiment to prevent any slipping incident. Make sure that the bar is untwisted before removing the clamp attached to it. And then ensure the diameter along the rod is uniform so that the result is not swayed. And then last, ensure there is no zero error on the calipers. That's all.